have seen how to write the transformation equations for stress. So I just recall the equations. So sigma x dash, for example, the transformed stress is given by sigma x plus sigma y by 2 plus and minus square root of sigma x minus sigma y by 2. Not this, sorry, this is plus cos 2 theta plus tau xy sin 2 theta and tau x dash y dash is given by minus of sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. And the principal stresses are given by sigma p is given by sigma x plus sigma y by 2 plus and minus square root of sigma x minus sigma y by 2 square plus tau xy square. And the maximum shear stress is given by square root of sigma x minus sigma y by 2 square plus tau xy square. Now, today we will solve a few problems of practical importance wherein this stress transformation equations are used. So the first problem which I have in mind is that of a simple beam which is bending under a load. So let's see, I have a cantilever beam which is of length L. There is a and free end load of P on it. So if I ask what is the principal stress in this beam at, let's say I draw the cross section here, and this is the cross section, and its width is B and its height is T. Now I say that from the neutral axis there is a fiber at a distance of y. So if I ask what is the maximum stress or the principal stress at y at the fixed end, which is here, this cross section is here, so what will be the answer? So obviously there are the bending stress because of the load is given by m upon I into y, which is m is equal to PL upon I is 1 by 12 Vt cube into y. That is nothing but 12 PL upon Vt cube into y. So that is the bending stress. Bending stress is compressive in the top fiber, it is compressive here, and it is tensile in the bottom fiber. Now the shear stress tau in the beam is given by Vq upon Ib, where V is the shear force which is P and I is 1 upon 12 Bt cube and B is the width itself multiplied by Q. Now Q at a distance of y from the neutral axis is the area, this area multiplied by the distance of the centroid of that area from the neutral axis. So that area is nothing but B multiplied by, that area will be T by 2 minus y, because this total is T by 2, because the total thickness is T, so half the thickness is T by 2, so that portion which is left around is T by 2 minus y multiplied by the distance of that centroid from the neutral axis, which is given by y plus half of that, which is t by 2 minus y by 2. So I simplify this equation, I get t minus 2y by 2 multiplied by this is 2y plus t by 2 minus y upon 2, which is nothing but b t minus 2y by 2 into 2y minus y is y, so it is t by 2 plus y by 2. So that is equal to b by 4 t minus 2y t by 2 plus y. I can of course convert this equation into b by 2. This will become t by 2 minus y t by 2 plus y. So that becomes b by 2 t square by 4 minus y square. So that's the value of q. So the shear stress at that location, tau will be equal to p, rather 12p upon b square t cube multiplied by this quantity. So the shear stress at that location, tau will be equal to Vq upon Ib. So we simplify the equation. The equation is 12p upon b square t cube into q. It is 12p upon b square t cube into q. Now q is nothing but b by 2 t square by 4 minus y square. B by 2 into t square by 4 minus y square. So that will be equal to 12p upon bt cube into, and this by 2 is also there, t square by 4 minus y square. So that is equal to 6p upon bt cube t square by 4 minus y square. Now that's the maximum shear, or that's the shear stress at that particular location. Now principal stress is given by sigma x plus sigma y by 2 plus minus square root of sigma x minus sigma y by 2 square plus tau xy square. So sigma x is given by we know how much the sigma x, it is I just write from the previous equation, it is 12pl upon bt cube y. So it is 12pl upon bt cube into y plus sigma y is 0, this divided by 2 plus minus square root of again the same quantity, which is 12pl y upon bt cube minus sigma y is 0 square, and this whole thing divided by 2 plus tau xy square, which is this quantity. So I just write it to tau xy square. Now you simplify this equation, we will get 6pl y upon bt cube plus minus square root of 6pl y upon bt cube square plus tau xy square. This equation can be simplified to get the value of maximum principal stress or minimum principal stress. So this is how the beam equation is solved, and the allowable value of stress is compared against this value which we get from here. This is how beam equation is solved. Similarly, I take the second example, which is of the torsion of the beam. Now torsion of the beam is I saw a very good classical example. I have a bar, circular bar, which has a handle here. There is a handle here, and at the handle I have a force being applied. So there is a force P being applied at the end of the handle. So let's say the handle length is L and the bar length is also L. Obviously handle is coming out in this direction, bar is in X direction, this is Y direction, and handle is in Z direction. Correct? Now let's say that the material of this is G and Young's modulus is E. So G is the shear modulus and E is the Young's modulus. Let us see how to get the principal stress for this case. Now this is a very good example because in this case we have all sorts of loadings. Now I isolate the bar, I apply this force can be transferred here P along with the torque. The torque is like this PL. Okay, and let's say that the radius is R, so the diameter is 2R. This is the torque. Now when this force is transferred here, the reactions will be TL and P. So there is a bending moment, there is a torque, and there is a shear force. Now, all the three forces are there in the problem now. That's a very complex and very good case to see the generalized conditions. Now in this case now, because this length is also L, so obviously the bending stress is again PL upon I into Y. Let's say the maximum stress will be R because the maximum Y will be R. Now this can be written as PL upon, now the I for circular cross section is pi by 4 R to power 4 multiplied by R. So that makes it 4 by pi PL upon R cube. That is the maximum bending stress in the bar. Now what is the maximum shear stress? Tau. Now so tau has two portions now. Tau is because of the applied force P directly. So the maximum value of that tau is at the center of the bar, which is given by 4 by 3 into P upon pi R square. Please remember for circular bars or for circular beams, the maximum shear stress is 4 upon 3 up of 4 by 3 times the average shear stress. This is the, if I draw the bar here again, this stress is here at this point, center, while that stress is here at the top and the bottom fibers, here and here. Because this is the maximum bending stress. Bending stress occurs maximum at the top and bottom fibers. So this is the location of maximum bending stress, while this is the location of maximum shear stress because of the shear force, applied shear force. Now besides this shear force, there is another shear stress which is because of the torsion, which is given by T upon J into R, which is nothing but T is PL upon J is pi by 2 R to power 4 multiplied by R. So that is equal to 2 PL upon pi R cube. So at this location, now I have to draw the cross section again. So I draw the cross section again here. So this is the cross section of the bar and this is the length of the bar. I'm just drawing a very zoomed up view. This is the center of the bar. This is the location of P and this is the torque PL and this is a fixity. Now at this point, let's say this is A and B, we have maximum bending stress. that is equal to 4pl upon pi r cube at A and B. I can just put plus and minus to show that at A it is minus and at B it is plus. Now at A and B, tau because of the P shear force is equal to 0, and tau because of torsion is equal to 2pl upon pi r cube. At A and B, this much torsion is occurring. At, I say this point is O, sigma B is 0. There is no bending stress at sigma at O, but tau P is equal to 4 upon 3 pi r square, and tau torsion is equal to again 0, because at O this is as a center, so there is no radius there. I mean, the value of radius is 0. Now you see, I can take 2 points here also, C and D. These points are at the same horizontal level as O, but at the diametral ends. At C and D, tau torsion will be equal to 2pl upon pi r cube. So now we have two conditions. We have rather two locations. We have a location A and B where the bending stress is high, but there is no direct shear stress. There is only torsional shear stress. We have points C and D where there is no bending stress, but there are two torsional stresses. And point O, there is only torsional stress. So at C and D, the total shear stress will be the sum of the direct shear stress and torsional shear stress. So that I just sum them up, it becomes 4 upon 3 P upon pi r square plus 2pl upon pi r cube, which is nothing but 2p upon pi. This goes out, this 2p upon pi goes out, so this becomes 2 upon 3. I can put r square also out, so 2 upon 3r. 2 upon 3, no r, yeah. Plus, so this 2p upon r square is out, so it is L upon r. That is the maximum shear stress which occurs in the bar at C or D. At A and B, sigma is equal to 4pl upon pi r cube. Now I haven't taken the sign of the stress. I always take the positive number because that will give us the maximum principal stress. And tau is equal to 2pl upon pi r cube. Now I have to figure out whether the principal stress is higher because of this or because of this. Whether this gives higher principal stress or that gives higher principal stress. So sigma p at A or B is given by sigma 1 plus sigma 2 by 2 or sigma x plus sigma y by 2. There is no sigma y, so only this by 2. So that becomes 4pl upon pi r cube divided by 2 plus minus, well, let's take the plus one only, plus 4pl upon pi r cube divided by 2 square plus tau square is 2pl upon pi r cube square. So this gives me, this becomes 2pl upon pi r cube plus this becomes square root of this becomes 2. So it is 2pl upon pi r cube, and this is also 2pl upon pi r cube. So it is 2 times 2pl upon pi r cube square. So it is 2 times 2pl upon pi r cube square. So that is nothing but 2pl upon pi r cube. This can be taken out from the square root sign, and the whole thing can 1 plus square root of 2. This is 1. This is from this. Okay. So I have, this is a principal stress at A and B, and the principal stress at C and D, because it's only pure shear, will be equal to this quantity itself. So sigma C D, or rather sorry, sigma principal at C and D, the principal stress at C and D, because there is only a shear stress occurring, so that itself will become the principal stress value. We know from yesterday that in case of pure shear, the principal stress is equal to the shear stress value only, and the shear stress value is 2p upon pi r square 2 by 3 plus L upon R. That is the value of the principal stress C and D. Now I write the principal stress at A and B again, which is nothing but 2pl upon pi r cube 1 plus square root of 2. So this is pi r cube, and this is actually 2pl upon pi r cube 2. So now let us compare which one of these is higher. Now I just say sigma p ab minus sigma p cd. I just say this. So if I do this, I get 2pl upon pi r cube 1 plus square root of 2 minus 2p upon pi r square 2 by 3 plus L upon R. So if I subtract this, see this 2pl upon pi r cube, and this is also 2pl upon pi r cube. So this term and this term gets cancelled out. Rather, I'll just say this term. So this becomes 2 square root 2 pl upon pi r cube minus 4p upon 3 pi r square. Now if I take again I take p 2 root 2p upon pi r square common, so this becomes L upon r minus square root 2 by 3. This is actually the same equation but written in a different form. So in this case, now we know that for this to be positive, for this quantity to be more than 0, we have to have L upon R greater than or equal to square root of 2 by 3. Normally this condition will be correct because L is far more than R. So this condition will always be true. So we know that the principal stress because of the bending will always be higher than principal stress because of the shear alone. In case of bars of long lengths and less small radius. Normally this condition will always be correct because we know that R is much smaller than the length. So normally L is much higher than R, which means L upon R greater than or equal to square root of 2 by 3 will almost always be true in practice normally. Okay, so hence in beams with torsion, principal stress due to bending will be greater than that because of torsion. So you see, this is why this chapter has been very, very important for us, because this gives us a very good insight into how uh, principal stresses, which are actually the ones which are compared against the material stiffnesses, are checked, and this is how we get the value of principal stresses in them. Tomorrow we will see the last part of this chapter, which is about the pressure vessels, and that's also very, very important chapter in my very, very important topic in my opinion. It's of extremely important practical consideration. It is used heavily in design of pressure vessels. Pressure vessels are those structures which have fluids stored at very high pressure, like gases or fluids and all that. So we will see them tomorrow.